to record the lecture. There we go. And then I'm going to switch to my iPad. There we go. And I hope this actually works. The computer has trust issues. There we go. Fantastic. All right. Very good. All right. So where we left off, if you can remember back that far, was talking about various ways to interpret this quantity that we had introduced called entropy. All right. So we were talking about entropy. Okay, and the way that entropy got introduced to us was essentially just fell out of the math when we were trying to determine what the most likely state of a system in equilibrium was going to be. And what we found was that this quantity, which we gave the symbol S, and which is equal to KB log omega. So the equilibrium state of your system is the state that maximizes this function. Okay, and then what we've been doing the past couple lectures is going through and giving various interpretations of what this thing means. All right, so last lecture we talked about entropy as disorder. Okay, so we showed that if you have a box or two boxes of gas, where you have one gas on one side and another gas on the other, and then you remove the divider between the two and let the two gases mix, then what you're doing is going from an ordered state where you have all the molecules of one gas on one side and all the molecules of the other gas on the other. You're going from that nice and ordered state to a disordered state where they're all mixed together. And as a consequence of that, you get an increase in entropy as a result of this mixing, which we showed was equal to N times KB times log of 2. Okay, and we showed that this quantity is equal to the entropy of what's referred to as a bit. That is, any system that can only has two states, and you can therefore encode information in a sequence of these two-state systems. Okay, then we also talked about black holes, right? So you remember we started this discussion talking about black holes, and that was kind of an introduction to thinking of entropy as a measure of information. Okay, and so today we're going to elaborate upon this idea, and specifically we're going to say it's a measure of information slash ignorance of information. All right, and you can already kind of see this from our discussion of the black holes. So what we had was a bunch of systems, whatever they were. So for example, we had our little boxes with gas in them, and each of these had some configurational entropy and momentum entropy and so on and so forth. And so we had, say we had a whole bunch of these little boxes. Okay, and so say this one had some entropy S1, this one had some entropy S2, and you can measure these boxes and see, for example, what all the different possible configurational states are and so on and so forth. Okay, but now what happens is that you have these observable systems that you can observe and actually measure the entropy of these systems, and what they're going to do is fall into a featureless dark black hole. All right, and so you can't, once it falls into this black hole, no information about these systems can ever be retrieved again. Okay, simply because the essentially the fastest way to transmit information is by light, and not even light can escape a black hole. So once these things fall in the black hole, they are gone forever. So you will never be able to measure anything about them ever again. All right, but now what we showed was that the black hole itself has entropy. Okay, and even though it's you know, it's about as dull of a system as you could possibly have, that is, it's just a big featureless black hole, it still has entropy. And where this entropy is coming from is simply all the things that fall into it are so you're losing all the information about the configurations of the things that fall into the black hole, and that loss of information contributes to the entropy of the black hole itself. Okay, does that make any bit of sense at all, I hope? All right, so now what we're going to do today is elaborate upon this idea. And it turns out that this formulation of entropy as a measurement of information or of ignorance of information is essentially the most general interpretation of entropy that you can come up with. Okay, so this is the most general interpretation. Okay, and you can even define entropy of things which don't even, physically exist. So what we're going to talk about today is, for example, if I sent, say, for example, a message to you by Morse code, so that Morse code message doesn't literally exist as any, actually physically observable system other than the electronic signals that are coming over the line to transmit that message. But as we'll show, you can still interpret that because that message encodes information, you can still say that that message has some entropy. All right, so that's what we're going to do today. Okay. All right, so now let's think about how you encode information. All right, so encoding information. All right, so let's say, for example, so like I said, let's say that I want to transmit some information to you by some signal, whether that's a electronic signal by Morse code, or it's a telegraph, whatever it is. Somehow what I have to do is transmit information to you. Okay, so now the way this was done before was by Morse code, right? So Morse code was made up of two symbols, dots and dashes. All right, so Morse code, you got two symbols, dots and dashes. So for example, if you wanted to transmit SOS, S is 3 dots, O is 3 dashes, and S is 3 dots. So you would do, 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 right? And by sending that sequence of dots and dashes, you're able to transmit information from one location to another. Okay, now notice, Morse code, you've only got two symbols, right? So every time I send a piece of information to you, that piece of information is either going to be a dot or it's going to be a dash. So again, it's two-state system. So Morse code is a two-state, not a system, it's a two-state code. All right, so in other words, it's behaving like a bit. Every time you receive a piece of information, it's going to be in one of two states. All right, so it's like a bit. It's either going to be on or off, a dot or a dash. Okay, so Morse code is a series of bits. Okay, now computers. The way computers currently do this is literally with bits. Okay, so they literally have little switches inside of them that can either be on or off. Okay, and if it's on, it's like, say, a dot in Morse code, and if it's off, it's like a dash in Morse code. And the way that you transmit these bits from one computer to another is just by essentially, it's like Morse code. It's just a series of electrical pulses over internet cables, essentially. But it's still the same idea. It's just a series of, high and low voltages, essentially. So the way this is currently done on computers is essentially high and low voltage signals. And again, two states, right? It's either high or it's low, two states. So this is also encoded in bits. Okay. So let's say, for example, I send you the code. Well, so let's say I would send you the code SOSO, just for reasons that'll become clear in a second. All right. So, and I send this by Morse code. So by Morse code, I can either, each letter is transmitted as a series of dots or dashes. So my information, once you receive a pulse of information, it's either going to be a dot or a dash. So for example, S is this. I shouldn't have these as dots. That's just going to make things confusing. So let me do it as boxes just to be clear what I mean here. So an S is encoded by 3 dots. So this is the S. The O is 3 dashes. So this is the O. And then the S is another 3 dots. Okay, and then the last O is again 3 dashes. And again, the reason it's SO will become clear in a moment instead of just SOS. It's because I want to be rigorously correct here. All right, so in other words, what I got here is 2 states. So I'm going to call the dots state 1 and dashes state 2. Okay, and my signal is made up of this series of state 1 signals and a series of state 2 signals. Okay, so now, let's say I want to assign. So I know this signal carries information, and I want to quantify how much information by calculating how much entropy this signal carries. Okay, so let's go back to our definition of entropy. So our definition of entropy is this, KB log omega. Okay, so again, what this omega is essentially the number of possible states your system can be in. So it's a number of so it's technically a density of states. So that's a number of states divided by a volume. But again, you have some quantity divided by another one. You can always, so all that volume is doing is again essentially setting the 0. So you can just ignore the volume essentially. So the entropy is related to the number of possible states your system can have. So for example, here our Morse code has 2 possible states. And so the entropy would be KB log 2, for example. Okay, so now let's think about this in a little bit more detail. So let's say in general we have, how do I want to say it? Let's say in general we have M states, M possible states. Okay, so for our Morse code here, M would just be 2. It's either dot or dash. All right. So now, and the simplest system that we are familiar with at this point is the microcanonical ensemble, right? So if we think about a microcanonical ensemble with M possible states, then every one of those states, by definition, if we're in the microcanonical ensemble, are equally likely, right? So in the microcanonical ensemble, all states are equally likely. With emphasis on the equally. So now maybe you can see why I did SOSO, because I want the probability of observing a dot be equal to the probability of observing a dash. All right. Okay, so in the microcanonical ensemble, the probability of observing any individual state, because they are all equal probability, is just equal to 1 divided by the total number of states, right? Okay, cool. Okay, so now let's go back to trying to calculate the entropy of this thing. So the entropy again is KB times the log of the number of states. Okay, so this is equal to KB log M, piece of cake. Okay, now, from right here, we know in the microcanonical ensemble at least, the probability of observing a state is simply related to the number of states that you have. It's just the inverse. Okay, so we can write this as KB log 1 over P sub I. Okay, and this is the same thing as KB log P sub I to the minus 1. And because of the properties of logarithms, we can just pull that minus 1 out front. So we get this, KB log P sub I. All right, so that's what we get for the microcanonical ensemble, is that the entropy of anything is equal to minus KB times the log of the probability of the states. And this is straightforward because in the microcanonical ensemble, the probability of every state is the same by definition, because it's related, the probability is related to the energy. They all have the same energy. Therefore, they must all have the same probability. Okay, so is this clear at this point? Is this making sense, I hope? Yeah? Anybody got any problems yet? All right, we got a thumbs up from Arturo. Excellent. All right, so now what I'm going to do is to try to generalize this. So now let's generalize. Okay, and the generalization I want to try to make is, what if I'm not in the microcanonical ensemble? Or what if I'm in the microcanonical ensemble, but we're not in equilibrium? Or what if I'm in a canonical ensemble or a grand canonical ensemble? That is an ensemble where the probability of all the different states are not equal. So let's generalize to non-microcanonical ensemble. Okay, i.e., that is, we want to generalize to where all the P sub I are not necessarily equal. Okay, so how do you do this? So I go back to this thing that I just derived for the microcanonical ensemble. And now the question is, if the P sub i's are not all identical, what do I plug in here for P sub I? Okay, and the answer is I'm just gonna make a guess, and it's gonna turn out that this guess is correct, again, because I'm the Cuisance heterarch and I know these things. All right, so what I'm going to say is that the entropy is equal to minus KB. And then, so the problem here is what am I going to use for this? And what I'm going to use is I'm just going to take the average. All right, so whatever the P sub i's are, I'm just going to plug in the various values of P sub I and then take the average. Okay, so in other words, I'm going to do this, log. So that's my generalization, is instead of using one specific P sub I, I'm going to look at all the different P sub i's and then just average them. Okay? All right. Okay, so now this is our general definition of the entropy. Okay, so in other words, what we're doing here is we're calculating the average, or as you may remember, we call this thing the expected value of log P sub I. Okay, so now I ask you to remember how it is that we calculate the expected value of anything, right? So the way that you calculate the expected value is of any function, f of x, assuming that your value of x is governed by some probability distribution, is that you take your quantity f of x, you multiply by the probability, so let's call this like this. You multiply by the probability of obtaining each value of x, and then you sum over all possible values. Okay, so we're going to write down exactly the same thing for this. Okay, so the way that we calculate this, S equals KB average of log p sub I. Whoops, I forgot a minus sign. Minus KB log p sub I is by this. Summed over all I. Okay, does that make sense? All right, so this is what we're after. This is it. So again, here these p sub i's are just referring to what is the probability of observing your system in state I. So if we go back up here to our Morse code example, this is again state 1, and so here p sub 1 for this would be 0.5. And for this, so not p sub I, p sub 1. So p sub 1 is equal to 0.5, p sub 2 is equal to 0.5. Okay, if I had just sent you the signal SOS instead of SOSO, so if I had just sent you this signal, then p sub 1 would be equal to, what is it, 6 over 9, and p sub 2 would be 3 over 9. Okay, so now what you would do to calculate the entropy of this signal is you would use these values as your p sub i's and simply plug them into this formula, and that will tell you the entropy, or that is the information, the amount of information that is carried in that signal. All right, this is referred to as the Shannon information entropy. Okay, so let me give you a trivial example. So let's say I send you this code. So again, I'm going to send it in Morse code. So my code is composed of a series of dots and dashes. Okay, but I've had a stroke or something, or, you know, I've passed out on the switch. Okay, and so all that happens is I just send a series of dots after dots after dots. Okay, so again, I've passed out on the switch. It just keeps sending dots. All right, now, how much information is carried by this signal? All right, so again, we got two states. We got state 1 and we got state 2. All right, but we only observe one of them. The only thing that you see is a series of dots. Okay, so the probability of observing dots is not 0, 1. Okay, so essentially for this signal, that's the only state you see. There is no other state. And how much information can you send in a signal composed of only one thing? You can't, assuming that, you know, they're all equally spaced, which is what's implied by the fact that they're dots, is they're all just dot, 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 dot. That cannot convey any sensible information. So let's take this and plug it in here and see what we get. All right, so the Shannon entropy that's carried by this signal is this, summed over all I, and that is minus KB times 1 times log of 1. And the log of 1 is 0. Okay, so in other words, this signal that's just made up of a series of equally identical repeating elements can convey no information whatsoever. And that fact, the fact that it can carry no information, is quantified by the fact that the entropy is 0. The more entropy a signal can carry, excuse me, the more information a signal carries, the more entropy it's going to have. So the amount of information is related to the entropy. It's directly quantified by the entropy of your signal. Okay. So does that make sense? All right, very good. So now, how does this relate to the entropy that we're all more familiar with? So let's say that we have a box, okay? And into our box, we place a bunch of gas molecules. Okay, and based upon the configuration of those gas molecules, you can calculate, the entropy of this system. So this system has some entropy, which is equal to KB log omega, which is KB log 1 over n factorial h to the 3n integral dp dq over all reasonable energy values. Okay, so how does this relate to what we just learned about entropy carried by signals? Okay, so what this number means, this is essentially, so what this number tells you is that information that would need to be transmitted to completely describe the configuration of your system. Completely describe your system. Okay, so if you got a box and it's full of gas molecules, and you want to, tell your friend, hey, I've got this box and it's full of gas molecules, and I want to tell you exactly everything about this box, then you would have to send a whole bunch of signals to your buddy describing for him exactly what the position of every molecule in the box is, what the momentum of every molecule in the box is, and the information that's carried, that would be carried by that signal from you to your friend to tell your friend everything about the configuration of that box. That is this number that we calculate like this. Okay, so whether you think of the entropy as the actual, related to the actual configuration or disorder of your system, or the amount of information that would have to be conveyed to somebody in order to completely describe your system, it's the same thing. Okay. All right. Does that make sense? More or less. And I think some of your homework problems this week have to do with calculating entropy of signals, and so hopefully you'll get a bit more experience thinking about these kinds of things. All right. So does that make sense? Does anybody have any questions about that? All right. I'll take that as a no. Okay, then we're going to move on to something else. We're going to start talking about something else today. Okay, so we've essentially now at this point introduced to you more or less all of the fundamental ideas of statistical mechanics. It's all about calculating volumes in phase space. The volumes in phase space are proportional to the probabilities, and from those probabilities and determining what the most probable state of your system is, the way that's done is by maximizing the entropy. Now, we've already gone through this. We've explicitly shown you how to do this and how to calculate these things for a classical ideal gas. And what we're going to start doing now is to take this system of ideas that we've put together and just start applying it to different systems to see what we can learn. All right, specifically what we're going to start talking about today is probably what you're all here for, and that is quantum statistics. Okay, and in the process of introducing quantum statistics, we're also going to introduce some other, I'm not going to say idea because it's still the same ideas. It's just another way of expressing the same ideas that makes the calculations more straightforward, I would say. Okay. All right, so now to introduce this idea, let's take ourselves back to our classical ideal gas. So for the classical ideal gas, you'll recall one of the questions we asked ourselves was, given that we have this box full of molecules, let's say we pick one of those molecules to measure it, okay? And what we wanted to measure was its momentum in one direction. So we asked, what is the probability of finding the momentum of a given molecule to have a specific value? And the answer that we got was that the probability of obtaining a molecule with momentum component, and we called it P1x equal to some specific value. What we got was that this was equal to, or was proportional to, e to the minus P1 squared over 2m 1 over kVt. Okay, now this, because it was an ideal gas, this thing here was just it's the kinetic energy of the gas, right? Specifically because it's an ideal gas and there is no potential energy, this is the total energy of that molecule of gas. So in other words, we could say that this was equal to e to the minus beta e, where e, well, I guess we should call it e star. E star was equal to P1 squared over 2m, and this beta is the inverse temperature, or the lazy factor, 1 over kVt. All right, so in other words, long story short, our answer was the probability of finding some state with energy E sub I is proportional to e to the minus beta E sub I. Okay. Okay, so now let's generalize this result, all right? So let's say we have a system, okay? So let's say we have a system that's composed of a collection of states, okay? So we have a system made of a collection of energy states and I'm going to call that collection of energy states the set E sub I. Okay. And then we ask ourselves again this question: what is the probability to find this system in one of these states, E sub I? Okay, so as we just showed, the probability is proportional to this. Okay. But now it's proportional, it's not equal. And the reason that it's not equal to this is because this is not normalized, right? So normalization insists that if we take these P of E sub I and we sum over all possible E sub I, that this should be equal to 1. Okay? So given that we know the probability of each state is proportional to this exponent, the way that we can make this an equal sign instead of a proportionality sign is just by normalizing it. Okay, so what we can do to make this an equal sign is, again, we take this factor that is proportional to the probability of our system, and then we divide that by the sum of all probabilities of our system. So we just sum over all possible e to the minus beta E sub I. Okay? And again, the reason we're doing this, so this is our normalization. This is just to normalize this thing. Okay, so now you can see that if you do this, so now if you take this and you sum over all I, obviously this is going to give you 1, right? Because when you sum over all E sub I, then what you get up here is the sum over all exponent of all E to the I divided by the sum of all E, so it's obviously 1. So it's obviously normalized. Okay? Now, Okay, so so now what we have is the probability of finding your system in any state E sub I is equal to, not proportional to, it is equal to this exponential factor divided by the sum of all possible values of this exponential factor. Okay, this is super important. This is what's referred to as the Maxwell-Boltzmann distribution. Okay, and again, this thing in the numerator, this is what's referred to as the Boltzmann weight of state I. Okay, so the weight is proportional to the probability to find it in that state. And to make that weight into an actual probability, you just divide by this normalization factor that is the sum over all possible Boltzmann weights. Okay, so does that make sense to everybody? All right. But now, so again, this thing in the denominator here, all this is a normalization factor, right? The only reason we put it in there is just to normalize things. But now it turns out that this thing is significantly more useful than just a normalization constant, okay? So this thing, that is the sum over all possible Boltzmann weights of your system, this thing is super important. So again, we introduced it just as a normalization constant. But it turns out that once you know this thing, you have become a god, right? Again, you're the Kwisatz Haderach. You know everything. You can see into the future, okay? So this, once you know this function for whatever system it is that you're talking about, you know everything about that system. And that's what we're going to spend the next few lectures showing you, is that once you calculate this thing, you are done, all right? So this thing is what's referred to as the partition function. Okay, and you give it the symbol capital Z. And holy crap, if you remember anything from this course, remember the partition function. Because like when you go take your physics GRE and they ask you any question that has anything to do with statistical mechanics, one of the first things you should ask yourself is, how do I calculate the partition function of this system? Because again, once you know the partition function, you are a god. You know everything. Okay. And again, what we're going to do is spend the next few lectures showing you how, once you know this thing, you know everything. All right, but for now, let's go back to our buddy here, the Boltzmann distribution. Okay, so now if I plot what this thing looks like, and again, so the Boltzmann distribution is this. The probability to find it in any state I that has energy E sub I is equal to e to the minus beta E sub I divided by the partition function. That is the sum over all e to the minus beta E sub I. Okay, but now what this corresponds to is that if I have a box, okay, and my box is full of molecules, each one of these molecules is going to have some momentum, right? And whatever value of momentum it has, that value of momentum corresponds to some kinetic energy. All right, so in other words, what I'm trying to say is that another way to express this probability is that this is also equal to the number of molecules that are in that state divided by the total number of molecules, which, you know, it's obvious enough. You just take the number of molecules that are in the state that you're interested in divided by the total number of molecules. That is the probability to find it in that state. Okay, so now, again, let me go back to plotting what this thing looks like. So what I want to plot is this number, n sub I, as a function of the energy, E sub I. And you can see that what this thing is going to look like, at least for high energies. So at high energies, what it's going to look like is a decaying exponential. All right, so if we go out to high energies, what the thing is going to look like is just this. So I'm going to say that is at high energies. It just looks like a nice decaying exponential. And you can do experiments, and you'll see that if you do experiments to measure what this is, it's beautiful. It works perfectly. Okay, but now the question is, what happens when you go down here to lower energies? All right, and when you go down to lower energies, that's when things like quantum mechanical effects start becoming more and more relevant. All right, and the reason for this is that, again, if you remember quantum mechanics, I mean, what quantum means is that the states are only allowed to have some certain allowed values of the energy. All right, so whatever system it is that you're talking about, if you plot what the energy levels are, they're going to look something like this. So at low energies, they're going to be spaced out pretty far. And generally, as you go to higher energies, they start getting closer and closer together until the point where you get to high enough energies, it's more or less just a continuous smear. All right, so it's in these regions of high energy where the energy levels are more or less continuous and a continuous smear that the Maxwell-Boltzmann distribution works fantastically. All right, but once you go down to lower energies, you cool things down. So, and what I mean by low energies is energies where the discreteness of the energy levels becomes more apparent. Okay, so in other words, you go to low energies where the discrete quantum mechanical nature of your system becomes obvious. That's when the Maxwell-Boltzmann distribution breaks down. So down here in this regime, this is where you expect quantum mechanical effects to start appearing. Okay, so now, so in other words, we already know everything about this region. All right, because quantum mechanics and classical mechanics, they all give you the same answer in the high energy regime. What we're going to start talking about next is the low energy regime. What do the statistics and the statistical mechanics of a gas, for example, look like at low temperatures where the quantum mechanical effects kick in? All right, so now, just again, to remind ourselves of some terminology, this lowest possible energy state of our quantum mechanical system, this is typically what you call E naught. This is the ground state of our system. And these higher energy levels, these are what are referred to as excited states. Okay, so now our general question is going to be, so for a quantum mechanical system, okay, so now what you can think of is each individual molecule that makes up this gas is going to sit in one of these energy values. So some of them are going to be, say, down here. Some of them are going to be at higher energy levels, like so. Okay, so certain number of molecules are going to be in the ground state, certain number of molecules are going to be at the first excited state, so on and so forth. Okay, and what we're interested in, generally speaking, for a quantum mechanical system, what are the occupation numbers of the ground state and excited states. Okay, so in other words, the things that we're going to, so for example, the way that I drew this here, the number of molecules in the ground state is 3. That was the wrong way to write this. So here N0 is equal to 3. And here N1 is equal to 2. And N2 is equal to 1, so on and so forth. But this is just one possible arrangement of the molecules within these energy states. I could have arranged it differently. All right. And each of those possible arrangements corresponds to one configuration of a quantum mechanical ensemble of states. And so what we're interested in is, on average, if we measure our gas that's at low energy state so the quantum mechanical effects are apparent, what are the expected or average occupation levels of occupation values of each one of these energy levels? So in general, the things that we're going to be after are these, the N sub I. Okay, does that make sense? Or I guess a better question to ask is, any questions? Okay, again, I'll take that as a no. All right, so just as an explicit example, let's recall a quantum mechanical harmonic oscillator. Okay, so quantum mechanical harmonic oscillator is where you take an atom or a molecule and you put it into a harmonic potential. Okay, so in other words, the potential energy for a harmonic oscillator is equal to 1/2 kx squared, or 1/2 m omega squared, or however you want to state it. So you have a quadratic potential. And you throw your molecules into this quadratic potential, and you want to find what are the available energy states, or what are the energy states that are available to these molecules. And I'm not going to derive it because, again, I assume you've taken quantum mechanics before. And as you've learned previously, the energy levels for a quantum mechanical harmonic oscillator are 1/2 plus n h bar omega, where n is some integer. Okay, and so now what we're going to do is, instead of just throwing one molecule into this quadratic potential, we're going to throw n molecules into this quadratic potential. Some of them are going to settle into the ground state. Some of them are just from random energy fluctuations are going to be at higher energy levels. So E0, that is 1/2 h bar omega, is the ground state. There's going to be some number of molecules in there. E1 is 3/2 h bar omega. There's going to be some number of molecules in there. Again, just from thermal fluctuations. And what we'd want to do is calculate, on average, what are these numbers? Okay. So that's our goal for essentially the remainder of this class, is to talk about the statistical mechanics of objects which obey quantum mechanics. It's going to be a blast. All right, so that's where we'll pick up on Wednesday. So does anybody have any questions about anything before I let you go? All righty-roo. Then we will call it quits there, and I will see you guys Wednesday at the same time. Adieu. I should really hold off on my silly saying goodbye until I am actually at the point where I can end the meeting. Okay, now, au revoir.